Okay, we're Group 13. I'm Peter. This is Allison and Alvin and Colin. And our toy is a mechanical walking crab. The motivation for this toy was it actually came from our toy design workshop earlier in the semester that we went to. We wrote down a lot of ideas, but this is one that we thought was one of the coolest. It may not have as many exciting surface features as other toys, but we were really interested in the motion as well. This design is based on the Colin linkage, and this linkage was actually designed somewhere in the early 90s, and it was designed to simulate certain animal leg movements. It actually has 5 bars, but technically it's a 6-bar linkage. It has 2 rockers, I think, and we had to modify the Colin linkage pretty iteratively for size and not to interfere with the body, because the original design doesn't really take into consideration that you're placing these next to each other, and it doesn't take into consideration the body that's supposed to be attached to. So originally the legs actually cross into the path of the body. We had to account for that. And the Colin linkage itself, the main purpose of it is so that for half rotation of the crank arm is a linear motion across the ground, and then the other half is a complete swing of the leg back to its original position. The idea being that you only need 2 to fully walk, but we figured we'd have 3 for stability. So that's the Colin linkage, and that's the main interesting motion of our toy. And Alvin will talk.
All right. So at first we actually thought about building a spider, but then we realized the way the legs walk are from side to side, and spiders usually don't walk from side to side, so we changed it to a crab. We also were planning on doing 8 legs, but due to volume constraints, which we'll deal with later, we changed it down to 6. It makes more sense for the crab. The first problem we dealt with was for the drive system. First dealing with the motor, because we have 6 sets of moving linkages. We need enough torque to overcome any friction that we're going to come across when moving all 6 of them. So that was problem with finding the motor. After that was down, we had to deal with getting gears to work. Gears were made in solid edge. They actually meshed really nicely. We're glad with how those turned out. Not too much we can show about those right now. And then the next problem was dealing with the camshaft. We needed to make sure the camshaft was able to connect to the gears and all 6 linkages. And then we also needed to make sure we could take it apart, so that because it's made in SLA, we can't make the gear or the legs directly onto the gear. So we need to piece it together piece by piece. So that gear is actually probably about 5 or 6 sections that are pieced together. And the gear is actually separate from that, or the cam. So that was another big problem we dealt with. And now Colin will talk about modeling.
All right, so modeling. Originally, we went with this crab idea. It was going to be really cool. Turns out that takes a lot of volume, and we chose a pretty large motor. So we ended up having to cut some material. But it turned out pretty cool, I think, because you can actually see all the internal stuff, and really the focus of this ended up being mechanical linkage and the motion. So having holes and all that ended up being a positive. The leg design is basically the most complex part of the surface modeling. It's done with swept blends and variable section sweeps, all sorts of good things. But we've done that all semester. You don't really care. The really difficult part was actually packaging. Because of the rotation of the camshafts, we have to account for that, as well as the gears that turn them. Again, this was somewhat driven by the size of the motor. Because it was reasonably large, we had to make gears that were big enough that when the cams rotated, they didn't interfere with the motor. So, we cut holes in the shell, basically. But it turned out really well, and Allison's going to talk about assembly stuff. Okay, so assembly. Let's run the analysis, actually. Let's do that. Yay. But as you can see, we actually did get the gears to mesh, which was a really big pain. It was really easy in that one example we did in class, but it took a lot of time to get it to work in our model.
Here you go.
We basically got the same motion that we're getting with our mechanism model out of our crab. It's just slightly wobbly due to the tolerances that we put in the pinholes. So there's a little bit of leeway in all the pinholes. So obviously it wobbles slightly, but it still gets the main points of the motion down that we want it to.
Yeah. All right, so assembly went reasonably well. We did have to do some sanding, as everyone else probably did. We used epoxy to basically stick the two halves of the shell together. We ended up actually not updating our STL file, so one of the parts didn't come out as supposed to, so the camshafts are held on with a ingenious method of space-age alloy and epoxy, also known as paper clips. But it worked out. It ended up working out perfectly, actually. The motor mount is pretty unique. You can kind of see it in there. We got the drawing of the motor from the supplier. It came with holes drilled and tapped in it, so we designed the mount to make that, and it worked out really well. It's perfect. Actually, the bolts went right in. And battery box purchased, batteries purchased, blah blah blah. We're gonna run it. We're gonna go over here so you can see it, because it actually does walk.
Colin, you want to do it here?
Huh?
So do it here so we can see it.
Sit if you're running.
Also, originally we had a switch, but it apparently didn't like DC voltage, so our switch is now removing a battery. So this is it actually working.
Pretty slow.
We chose a motor that's really, really low RPM but really high torque, again, because we were concerned with all the friction of all the joints. But it walks.